In chapter 2, we're going to be looking at basic topology. And this first section, as you can see, talks about finite, countable, and uncountable sets. And this section has a bunch of definitions really, just so that we know what terms are that we're going to use later on. So for example, we can start with a box that has a total of 5 definitions. So consider two sets A and B, whose elements may be any objects whatsoever. And suppose that with each element x of A, there is associated in some manner an element of B, which we denote by f of x. Then f is said to be a function from A to B, or a mapping of A into B. The set A is called the domain of f. We also say that f is defined on A. And the elements f of x are called the values of f. The set of all values of f is called the range of f. So as you can see, it's 5 terms that you probably already knew from either, if not high school, then undergrad, or your first math classes. So it shouldn't be anything new. And same thing with these next definitions. Let A and B be two sets, and let F be a mapping of A into B. If E is a proper subset of A, or just a subset of A, f of E is defined to be the set of all elements f of x for x in E. We call f of E the image of E under f, and in this notation, f of A is a range of f. It's clear that f of A is a subset of B, and if f of A is equal to B, we say that f maps A onto B. So there's a little distinction between onto and into. Okay, next definitions. If E is a subset of B, f, that notation there, denotes the set of all x in A such that f of x is in E. We call that notation the inverse image of E under f. If y is in B, the inverse image is a set of all x in A such that f of x is equal to y. If for each, I forgot to put something there. We're missing a y. If for each y in B, the inverse image of y consists of at most one element of A, then f is said to be a one-to-one mapping of A into B. And our last definition for this slide, if there exists a one-to-one mapping of A onto B, we say that A and B can be put into one-to-one correspondence. You might know that as a bijection, or that A and B have the same cardinal number, or briefly that A and B are equivalent. And we write A with that squiggly to B, A is equivalent to B. This relation clearly has the following properties. It's reflexive, it's symmetric, and it's transitive, right? And you should probably already know that these 3 properties together make up an equivalence relation. So I'm going a bit fast because these shouldn't be new definitions. The ones you might have not gone over too much are this next one, or these next definitions. For any positive integer n, let J sub n be the set whose elements are integers 1 to n, and let J be the set consisting of all positive integers. For any set A, we say A is finite if A is equivalent to J sub n for some n. So just as your intuition would tell you. In this case, I just want to point out J we're using to pretty much mean positive integers. You might know those as the natural numbers. In this case, we're using uppercase J. So it's just different notation. Don't let that confuse you. So B, A is infinite if A is not finite. A is countable if A is equivalent to J. Right? So these numbers, 1, 2, 3, so on and so forth, those numbers are countable. Okay? A is uncountable if A is neither finite nor countable. A good example would be the real numbers. The real numbers are uncountable. A is at most countable if A is finite or countable. So a set with just 1, 2, 3 would be at most countable. Same as a set J, it is at most countable. Countable sets are sometimes called enumerable or denumerable. Here's a little example. Let A be the set of all integers. We can show that that is countable, right? And we just consider the following arrangement of the sets A and J. So here, 1 with 0, 2 and 1, 3, -1, 4, 2, 5, -2, 6, 3, 7, -3. And we just continue in that fashion. So next would be 4, -4, 5, -5, so on and so forth. And we could always do a bijection, a one-to-one correspondence between A and J, thus showing that A is countable. Okay, sequence. Maybe you've seen this in a previous analysis course, an introductory one, or even in calculus. Maybe, right, so a sequence, we mean a function f defined on the set J of all positive integers. If f of n is equal to x of n for n positive integer, it is customary to denote the sequence f by the symbol x of n with the little brackets, or just sometimes by x of 1, comma x of 2, comma x of 3, so on and so forth. The values of f, that is the elements that x of n outputs, are called the terms of the sequence. If A is a set, and if xn is an element of A, for all n in J, then x of n is said to be a sequence in A, or a sequence of elements in A, of A. With that, you should probably know what a subsequence is as well, which just pretty much means taking some terms of the sequence, making a new sequence. But we come up with a theorem that says every infinite subset of a countable set is A is countable. And here I mentioned subsequences because we will be using, to prove this, we will be using subsequences. So first, suppose E is a subset of A and E is infinite. Well, we're going to arrange the elements of X of A in a sequence of distinct elements. And ignore this little period here. So we're just going to arrange the elements X of A in a sequence. Well, we can construct a subsequence or a sequence n sub k as follows. Let n1 be the smallest positive integer such that x sub n sub 1 is in E. Having chosen n sub 1 all the way to n sub k minus 1, where k is 2, 3, 4, so on and so forth, we let n sub k be the smallest integer greater than n sub k minus 1 such that x sub n sub k is in E. All that's saying is try to get all these terms, including n sub k, as close as possible, still in order, but as close as possible to each other. Don't just choose another term in the sequence that's just greater than it. Try to make it so that it's just the next one in the sequence. That's what it's saying. That's why it's the smallest integer greater than n sub k minus 1. For example, if I was constructing the sequence positive integers 2, 3, I wouldn't just go to 8 and then 12 and then 1,000. I would want to go 1, 2, 3, and again the smallest integer that's greater than 3. So probably not 8, but 4. Smallest integer greater than 4, 5, and this way I just go in order. So that's what this is doing, that subsequence. While putting f of k as a subsequence x sub n sub k, we obtain a one-to-one correspondence between E and J, thus proving our theorem. Okay, the next slide has pretty much just two definitions, but they're big ones. And it's just because of notation. So let A and omega be sets, and suppose that with each element alpha of A, there's associated a subset of omega, which we denote by E sub alpha. The set whose elements are the sets E sub alpha will be denoted by E sub alpha with brackets. And instead of speaking of sets, we're going to sometimes speak of a collection of sets or a family of sets. And the union, the way we just write the union of these sets, E sub A, is defined to be the set S, such that X is in S, if and only if X is in E sub alpha for at least one alpha in A. So S here, I know it might sound confusing or a lot of information. It's just a collection of sets. It's the union of sets of E sub alpha. Here's another way to denote it. We can write this when A consists of integers 1 to n. Or we can simply write it like this, if it makes it easier to see. And then if n goes all the way, or m goes all the way to infinity, we'll just write it like this. And it's pretty much the same for intersections. Now we're using P. So P is the intersection of all these sets. Another way you can write it, same as the union for integers 1 to n. But if it goes to infinity, we can write it like this. And last thing, if A and B, if their intersection is not empty, we say that A and B intersect, so they're not disjoint. So some examples of this is, suppose E1 consists of 1, 2, 3 of that set. I should have probably written or given them a bracket to denote a set. E2 consists of 2, 3, 4. Then their union consists of 1, 2, 3, 4. Again, some brackets here. But the intersection is only 2 and 3. Those are the only elements they share. A more interesting example, we're going to let A be the set of real numbers x such that 0 is less than x and x is less than or equal to 1. For every x in A, let E sub x be the set of real numbers y such that 0 is less than y, which is less than x. Well, then we get that E sub x is a subset of E sub z if and only if 0 is less than z and x is less than, 0 is less than x and x is less than or equal to z, which is less than or equal to 1. That one's pretty obvious, shouldn't be too hard to see. You can just draw a real line. Here we have the union of all the sets of E sub x, which should be E sub 1. Or, yeah, right. Which should just equal E sub 1. And this next one is probably the one that's least obvious, but it still shouldn't be too hard to see. The intersection of all the sets E sub x is empty. This one may require a proof to show it, but again, it shouldn't be too hard to see. Okay, now we come to a theorem that says let E sub n where n goes from 1 to infinity, be a sequence of countable sets, and put S to be the union of those countable sets, then S is countable. So it's pretty much saying the union of countable sets is countable. So the way we prove this, all we're going to do is follow something like this picture. We're going to follow a sequence in that manner. So let every set E sub n be arranged in a sequence x sub nk, where k goes from 1 to infinity. And we consider the infinite array in which elements of En form the nth row. So just as the picture shows, we would write that out. The array contains all elements of S, so all the elements here. We can use them all up using these arrows. So we're going to arrange these in a sequence. So first, we go x sub 1, 1, 1, and then x sub 2, 1, x sub 1, 2, and then x sub 3, 1, x sub 2, 2, x sub 1, 3. We just keep going on and on. So these arrows would keep going like this, so on and so forth, right? We arrange them in a sequence looking like this. If we do have that any of these in here, any two are the same, any elements are the same, that's an ugly arrow. Any two elements are the same, that will appear more than once in the sequence, that's no problem. Well, therefore, there's a subset T of the set of positive integers such that S is equivalent to T, which shows that S is at most countable. And since E sub 1 is a subset of S, and E1 is infinite, S is infinite, and therefore countable. We have some little theorems that come with it. These aren't, the proofs aren't too important for understanding of analysis, so I'm just going to mention the theorem. We also have a corollary. So this one says let A be a countable set, and let B sub n be a set of all n tuples. A sub 1 out of the way, A sub n, where A sub k is an element of A. And the elements A sub 1 to A sub n don't need to be distinct. Well, B sub n is countable. That shouldn't be too hard to see. And then the corollary tells us that the set of all rational numbers is countable. You might have seen that proof before. We're actually going to be looking at an interesting on this last slide. So let A be the set of all sequences whose elements are the digits 0 and 1. This set is actually uncountable. And the elements of A are sequences like this one that I'm showing here. This is just one of the sequences. 1, 0, 0, 1, 0, 1, 1, 1, so on and so forth. Well, how do we prove that this is uncountable? First, we let E be a countable subset of A. And let E consist of the sequences S1, S2, S3, so on and so forth. So for this, we're going to then say that we can construct the sequence S as follows. And the nth digit, S sub n, is, in S sub n, So if in the nth digit S sub n is 1, we change that digit to 0. Or if it's 0, we change it to 1. Right? So for example, if I had this sequence and say in S sub 2, I would change this 0 to a 1 to now have the sequence 1, 1, 0, 0. That's what that's saying. So then the sequence S differs from every member of E in at least one place. So S can't be an E, right? So S differed from S sub 2 in the second place. It differs from S sub 3 in the third place, so on and so forth. So S can't be an E. That sequence S cannot be an E, but clearly S is an A, right? Because it's a sequence of, well, of just the digits 0 and 1. So E is a proper subset of A. And we've shown that every countable subset of A is a proper subset of A. So it follows that A is uncountable. Otherwise, A would be a proper subset of A, which is pretty just absurd. Therefore, this set A is uncountable. And this method was actually introduced by a famous mathematician. Maybe you've heard of him. Let me just erase this. His name was George Cantor. You might know the Cantor set. Maybe you've heard of it. But he was central to the theory of math. He created set theory, which a lot of mathematicians say it's a fundamental theory in math. And he was German, and he came up with this clever form of proof. And we're actually not done talking about him for this class. We're going to be looking at Cantor sets and other different things that he came up with that are really interesting. So